So the next talk is Endemic Oblivious Transfer via Random Oracles Revisited. It's by Zhelei Zhou, Bingcheng Jian, Hongsheng Zhou, and Gui Ren. And Zhelei Zhou is going to give the talk.
Okay, thank you. Hi everyone, this is Zhelei Zhou, a PhD student from Zhejiang University. And the topic I want to share today is Endemic Oblivious Transfer via Random Oracles Revisited. It is a joint work with Bingsheng Zhang, Hongsheng Zhou, and Kui Ren. Oblivious Transfer is a fundamental cryptographic primitive, and it is widely used in the MPC areas, such as the famous Yos-Gablet circuit and the GMW protocol. In the standard 1 of 2 OT, there is a sender and a receiver. The sender will input two messages, M0 and M1, and the receiver will input his choice bit. And at the end of the protocol, the receiver will obtain MB without knowing the other message, and the sender cannot tell which message was received by the receiver. Recently, Mezzini and Rindo proposed a new OT notion called Endemic OT, short for EOT. In EOT, the sender has no inputs, and at the end of the protocol, the sender will receive two messages, M0 and M1. In the case where both sender and receiver are honest, these OT messages should be uniformly random. However, the situation is different when in the malicious case. In the case where the sender gets corrupted at first, the malicious sender can specify its output. Similarly, when the receiver gets corrupted, the malicious receiver can also specify its output. So in a word, EOT can be viewed as a weak version of OT, where the adversary can fix its output arbitrarily. And some of you may wonder why EOT is so interesting for us to study. And here I give you a concrete EOT example, which was proposed in MR19. As you can see in the picture above, the messages between there is no dependency between the messages, sender's message and the receiver's messages. Therefore, these messages can be sent simultaneously together. In other words, the word in which message is sent first is not important. As you can see in the picture above, in this protocol, we let the sender send their message first. Actually, this protocol would also be secure if we let the receiver send their messages first. So that's why only one round communication is required. Another appealing advantage of EOT is that it can be made truly practical in both computation and communication aspects. So that's why we study EOT. And in this work, we mainly focus on EOT via global random oracles. So I will first introduce you some background knowledge about local random oracle in the UC framework and the global random oracle in the GUC framework. Next, I will show you our new EOT constructions. And in this talk, I will only give you one construction, and others can be found in our paper. And finally, I will introduce you some relations we explored in this work. Okay, now let us first enter part 1, background knowledge about the random oracle. Random oracle is a popular idealized setup which enables truly practical EOT protocols. And in the UC framework proposed by Rankinadi, the random oracle is only local to the protocol instance, and therefore the random oracle can be simulated by the simulator. And this grants the simulator two advantages, namely observability and programmability. Observability means that the simulator can see the queries by anyone. And the programmability means that the simulator can determine the answers of the queries sent by anyone. So in a word, random oracle serves as a local setup in the UC framework. And the situation is different when we turn to generalized UC, short for GUC framework. As you can see, in the GUC framework, the random oracle now external to the simulator, and the random oracle serves as a shared setup that can cross multiple protocol sessions and can be accessed by the environment directly. And therefore, random oracle becomes global and cannot be simulated by the simulator anymore. And in this work, we will mainly focus on the global random oracle, since it is a more realistic setup assumption compared to local random oracle. And more precisely, we will focus on two global random oracles in the literature, namely the Global Restricted Observable RO, short for GRRO, which allows the simulator to see the adversary's queries, and the Global Restricted Programmable RO, short for GRPRO, which allows the simulator to program the unqueried points without being detected. And it is known that when simultaneous communication model is loaded, it is possible to give one round EOT constructions. And here we list at least three state-of-the-art EOT protocols in the literature, and they are all built on the local setups. Particularly, I want to point out the protocol proposed in MR19 was established under non-standard assumptions. Therefore, it is natural for us to ask, is it possible to give one-round GUC-scale EOT constructions under standard assumptions in the global random oracle models? And we answer these questions by showing that one-round construction is possible in the GRL model, and two-round EOT construction is possible in the GRPL model. And in our paper, we showed that one-round GUC-scale EOT protocol is impossible in the GRPL model. Therefore, both of our constructions are round optimal. Besides constructing EOT in the global random oracles, we are also interested in the complexity, including the power and the limits of the EOT itself. Namely, we wonder what's the relation between the EOT and other cryptographic primitives. And we are also interested in the global random oracle we used in this work, and we wonder what's the relation between these two global random oracles. And in this talk, I will first answer our first research questions in part 2 and answer the rest of the research questions in part 3. Now let us enter part 2, new constructions. And in this part, I will give you our one-round EOT constructions in the GRL model. And we start with the two-round standalone EOT protocol in the local RO model, which was proposed in CO15. And in such two-round protocol, the sender will first compute a random group element H and send this group element H to the receiver. Upon receiving H, the receiver will use it along with the common group element G as the commitment key to compute a Patterson commitment instance to its choice bit and send the Patterson commitment back to the sender. Finally, both the sender and the receiver will perform some local computation to obtain their local OT messages. And our goals are to reduce the round complexity of this protocol to one round and further make it GUC secure in the GRL model. So, to achieve our first goal, we let the receiver locally generate the commitment key by invoking the random oracle on a randomly selected string. And in this way, the receiver can locally compute the Patterson commitment key, Patterson commitment without relying on the sender's messages. And in this way, one-round communication can be achieved. And this technique was inspired by CSW20. And next, how to achieve GUC security. And in order to achieve this goal, we observe that it requires both sender and receiver additionally generating the straight-line extractable non-interactive witness hiding arguments. And these underlying arguments provides extractability for both sender and the receiver, and therefore provides the GUC security. And these underlying arguments can be obtained from Sigma protocols. And that's how we construct our EOT protocol. And next, I will provide you an informal security analysis about why this construction is secure. So let us first consider the case where the sender gets corrupted first. And in this case, the simulator has to simulate the honest receiver and has to extract the randomness from sender's messages. And we observe that this can be done by making use of the straight-line extractability of the underlying arguments. And the straight-line extractability relies on the restricted observability of the GRL model. And so in a word, the simulator can extract the sender's randomness since it is allowed to see the malicious sender's queries to the random oracle. And when we turn to the case where the receiver gets corrupted, the situation is quite similar. And in this case, the simulator has to simulate the honest sender and has to extract the receiver's choice bit from the receiver's messages. And the security analysis was quite similar to the previous case, and that's how we accomplished the security analysis of this protocol. And finally, we arriving at the part 3, new theory. Recall that previously we want to ask, what's the relation between the EOT and other cryptographic primitives? And actually, in MR19, Messny and Rindo have already initialized the investigation of these research questions. More precisely, they proposed a new OT notion called uniform OT, short for UOT. UOT looks very similar to EOT, except that in UOT, the adversary cannot have any influence on the OT's messages. In other words, these OT messages should always be uniformly random. So obviously, UOT provides stronger security guarantees than EOT. And they also discovered that UOT implies EOT, and UOT can be built from EOT and coin flipping unconditionally. However, whether EOT implies UOT remains unknown. And in this work, we will show you that EOT actually implies coin flipping. So therefore, EOT implies UOT. And we start by showing that EOT implies bit commitment. And our construction was inspired by BFSK11. Recall that in BFSK11, the authors showed that the standard 102 OT implies bit commitment. And in this work, we observe that the 102 OT can be replaced with the EOT. And we present our constructions in the picture above. As you can see, in the committing phase, the committer will play the role of the EOT receiver, and the receiver will play the role of the EOT sender. And at the end of the committing phase, the committer will receive his OT messages MB, which will be used as the opening message later in the opening phase. And this construction is quite simple, but it is secure, and I will show you why this is secure. Typically, a commitment protocol requires two properties, namely hiding property and binding property. And we will observe that if the malicious receiver can break the hiding property, which means the malicious receiver can tell which OT messages was received by the committer, then we can build a reduction to break the EOT receiver's security. Similarly, if the malicious committer can find a way to break the binding property, which means the malicious receiver can find a way to obtain both OT messages, then we can build a reduction to break the EOT sender's security. And that's how we prove our commitment protocol is secure. So we have already showed that EOT implies commitment, and it is well known that commitment implies coin flipping. And combine these results together, we show that EOT implies UOT. And there is also a side product here. And in this talk, I have already show you one-round GUC secure EOT constructions in the GRR model. And by our bit commitment constructions, we will immediately obtain a two-round GUC secure commitment in the GRR model. And here I compare our commitment construction with other state-of-the-art GUC secure commitment in the GRR model. And as you can see, even if previous constructions requires weaker computational assumptions than this work is the only one that can achieve two-round communication by assuming simultaneous communication model. And finally, let us explore the relation between the GRR model and the GRPR model. In this talk, I have already shown you that one-round GUC static secure EOT is possible in the GRR model. And in our paper, we discovered that one-round GUC static secure EOT is impossible in the GRPR model. And therefore, we show that GRPRO does not imply GRRO. And however, whether GRRO implies GRPRO remains unknown. Okay, finally, we are arriving at the conclusion part. And in this talk, we first constructed round optimal EOTs in the global random oracles. And in this talk, I only give you our GRR-based constructions. And our GRPR-based constructions can be found in our papers. And here I compare the efficiency of our EOT protocols with other state-of-the-art protocols. As you can see, the efficiency of our GRPL-based constructions is competitive. Meanwhile, the efficiency of our GRL-based construction is not so competitive, but it's requires weaker computational assumptions than others. And I have to also to point out that both of our constructions are GUC secure, while others are only UC secure. And in this work, we also investigate the relation between EOT and others. We discovered that EOT implies commitment and EOT implies UOT. Combined with the result in MR19, we showed that EOT and UOT are information theoretically equivalent. And finally, we investigated the relation between GRL model and GRPL model. We showed that GRPL does not imply GRL. However, whether GRL implies GRPL remains an open question. And that's all. Thanks for listening.
Any questions? You said that you also had some results in the local random oracle model?
Yes.
How does that compare with the constructions in the...
Yes, in this talk, I didn't give our constructions in the local random oracle models. This can be found in our papers. And the efficiency of our local RO-based constructions is not so competitive to MR19, honestly. However, as I mentioned before, the protocol in MR19 was established under non-standard assumptions, while our local RO-based constructions was under standard assumptions, namely the DDH assumption. So I think this is the advantage of our local RO-based constructions.
Okay. Well, if there are no more questions, let's thank the speaker again. Yeah, the next talk will be a new framework for quantum oblivious transfer, as work by Amit Agarwal, James Bartusek, Dakshita Kurana, and Nishant Kumar. And James Bartusek will give the talk.
Okay, thank you. Yeah, so this is a new framework for quantum oblivious transfer. Joint work with Amit, Dakshita, and Nishant. So tragically, Nishant has since passed away. Nishant was a wonderful collaborator and friend, and our work in this talk is dedicated to him. So let me begin with some background. And I'll start with kind of where it all begins with Stephen Weisner's paper from 1968 that basically started the area of quantum cryptography. And in this paper, he promises to study a method of encoding, or a type of coding scheme that's only made possible by the uncertainty principle and has no classical analog. And the first example he gives for its usefulness is a means of transmitting two messages, either but not both of which may be received. And so these days we know this as Oblivious Transfer. And so he basically, in this paper, introduced this notion that he called conjugate coding. And the basic idea is that if a sender has two messages, you can maybe think of these as just 2 bits, M0 and M1. They can transmit one in the standard basis and another one in the Hadamard basis. And the point is that if the receiver has their measurement device set to kind of measuring in the standard basis, then they will learn M0, but nothing about M1. Their measurement will kind of destroy all the information about M1. On the other hand, if they have their measurement device set to measuring in the Hadamard basis, they'll learn M1 and nothing about M0. Right? So this is the basic idea. Clearly, it's insecure against general or like malicious receivers that may decide to measure different qubits in different bases. Wisner talks about kind of permuting these qubits around to try to block this attack, but he also acknowledges that there are probably more general attacks, okay? Which there are. But this idea, nonetheless, was extremely influential. And the first work after Wisner to really study the use of quantum communication in OT was Krepo and Killian in '88. And they added two components to Wisner's proposal, namely interaction and cryptographic bit commitments, to obtain a protocol that is plausibly secure, okay? Although they did not prove its security. In fact, it wasn't until many years later these works made some real progress in the security of the scheme by showing that this template is secure when the commitment that is used is ideal. And by ideal commitment, I mean one that satisfies both equivocality and extractability. Okay? And then a couple of concurrent works, recent concurrent works, one of, so Grillo, Lin, Song, and Vaikunth-Nathan, constructed post-quantum ideal commitments from just one-way functions, which then establishes OT from one-way functions, plus quantum communication. A concurrent work of myself, Coladangelo, Karana, and Ma, constructed post-quantum ideal commitments just from the black box use of standard commitments, by which I mean just commitments that are statistically binding and computationally hiding. Right, so if we go back to this Krepo-Killian template and look at this component of a commitment, right? By now we really understand this part of it. So we know that some cryptography is necessary, and this was proven in the 90s, at least so. Some cryptography is necessary for OT, right, even if we use quantum communication. And by now we know that standard commitments are sufficient, kind of one of the weakest cryptographic primitives you can imagine, right? So the focus of this talk is going to be on this other component of interaction. I think we know less about this. Is it necessary? If so, how much interaction is necessary for quantum OT? Okay. So what's known about interaction? Well, like I said, Wisner proposed a non-interactive protocol, just one message from sender to receiver, but it's insecure. If you write down the template proposed by CK88, you'll probably see that it's 7 messages, assuming the ideal commitment that they're using is non-interactive. Okay. Although these works that kind of construct these ideal commitments are in general polynomial rounds in the plane model. GLSV also gives a constant round protocol in the common random string model, but they leave the number of rounds unspecified. It's going to be definitely at least 7. So this is what was kind of known prior to our work. Okay, so this is the question we ask, how much interaction is really required for quantum oblivious transfer? And what exactly do I mean by quantum oblivious transfer? The name I find fairly confusing, but it's become standard. It's an OT protocol that, so it's a standard OT protocol, right? But it makes use of quantum communication, but no public key cryptography, right? And so why do we study this object? Because without quantum communication, it's widely believed, and there's evidence for the fact that public key crypto is necessary for OT. So if we want to relax the use of public key crypto, we're going to have to add in some quantum communication. Right? So our results are stated as follows. We're going to capture the notion of symmetric key crypto or non-public key crypto by designing protocols that are in the quantum random oracle model and use no other assumptions, right? So we just want to assume some idealized usage of a hash function and nothing else. And our first result is a 3-message kind of standard chosen input string OT protocol, right? So sender has messages M0, M1. A receiver has a choice bit B. They interact in 3 messages, and the receiver obtains message M sub B. Okay. And then our second result, we study a bit of a different setting, okay, where we assume the sender and receiver start the protocol with some pre-shared entanglement. In particular, we just assume that they share some number of EPR pairs. Okay. And in this setting, we can actually get a 1-message protocol, fulfilling Wisner's original vision, at least when the sender is just transmitting bits. So if M0 and M1 are just bits, they can send one of these 2 bits to the receiver, and the receiver will obtain a MB for a uniformly random chosen B. Okay? Good. So let me talk about a little bit about the techniques we use to get these results. And our starting point is actually we go back to Wisner's original protocol, which recall is basically having the sender transmit one of their messages in the standard basis and the other message in the Hadamard basis. Okay? And the issue here, and kind of what we need to overcome, is how can we guarantee that the receiver measures both of these states in the same basis, right? It doesn't matter which basis, right? Like if they measure both in the standard basis, then they'll necessarily be losing information about M1. If they measure both in the Hadamard basis, they'll necessarily be losing information about M0. So what's really important for us is to guarantee that they pick one of these two bases and measure both qubits in that basis, right? So roughly how we accomplish this is as follows. So I'll give like a high-level picture of what the three messages of our protocol look like. Our first message is basically just a parallel repetition of Wisner's proposal using just like encoding random bits. Okay, so like in each column you can see, or in most of these columns you can see that one bit is encoded in the standard basis and one bit is encoded in the Hadamard basis, except for a couple of positions that we call trap positions, right? Where the sender is actually just going to sample a uniformly random basis, one of these two bases, and encode bits in the same basis. Okay, and we call these positions just trap positions because they're going to be used to make sure that the receiver is indeed measuring each of these columns in the same basis. Okay, and our second message is basically the receiver accomplishes a proof that the receiver has done this, at least for most of the columns, right? So they measure each pair of states in a basis of their choice, and then prove this fact using what we call a non-interactive measurement check subprotocol. Okay? And then the third message, the sender will use the random bits in the non-trap columns to actually mask their messages M0 and M1 and transmit this to the receiver. Right? So this is the very like, high level of what the protocol looks like. We call this the fixed basis framework for OT because our first message consists of pairs of states in these fixed bases, right? Everyone knows that like the top state is going to be in the standard basis, the bottom state is going to be in the Hadamard basis, of course, except for these interspersed trap positions. And we call it this to differentiate it from CK88 template and all the follow-ups that basically begin with the first message that encodes a bunch of random bits in random bases. Okay. And it turns out that doing this necessitates some extra interaction, which we're able to remove using this framework. Okay, and let me say a few more words about this non-interactive measurement check subprotocol, or at least the building blocks that we need to use to construct it. So the first component of it is a commitment scheme where basically the receiver like measures all these states and commits to all their measurement results. And we need to use an ideal commitment. And so we need to formalize an ideal commitment in the quantum random oracle model. Okay? And the construction is basically what you'd expect, just like in the classical random oracle model. You basically hash the bit you're committing to along with some randomness. But formalizing that this is extractable builds on some recent work by Zandri and then Don Fair, Mayens, and Schaffner on online extractability in the quantum random oracle model. Okay. And to make this measurement check subprotocol non-interactive, we're going to apply basically a Fiat-Shamir step where we like hash all these commitments to give us a subset that the receiver is supposed to open and send back to the sender. And so to argue the security of this, we're going to combine some recent work on the post-quantum security of Fiat-Shamir with BF10 kind of OT proof techniques. Okay? And so I encourage you to see the paper for further details about that. And then moving on to our next main result, right, I'll just say a few words about this. We take our three-message protocol and essentially compile it to a one-message protocol in the shared EPR pairs model by replacing that first quantum message with shared EPR pairs, removing the third message, which basically switches the roles of the sender and receiver and makes one of their inputs random. And then to kind of switch these back, we're going to apply a non-interactive OT reversal protocol due to Shai, Kilian, Nissim, and Petronk. Okay. And let me say some words about one like kind of crucial technical tool we need when we compile to just a one-message protocol. It turns out that like all prior work on OT uses some randomness extraction to basically hide the sender messages, right? And they use a seeded extractor. Okay. But when we move to one message, we can no longer use a seated extractor. We just don't have enough interaction to enable that. And so we need a unseated extractor. And it turns out that just XOR works, at least for this quantum source of entropy that we need. And so the lemma that we prove is we say, well, consider any two-register quantum system on A and B that satisfies the property that the state on system B is only supported on standard basis states with low Hamming weight. Okay? And what we want to do is measure this system, all these qubits in the Hadamard basis, and XOR the resulting bits together to get a single bit, little b. Okay, so intuitively, little b should have a lot of entropy. And what we can show is that even conditioned on some arbitrary system A that might be arbitrarily entangled with B, system B, that the bit little b is actually uniformly random, even given knowledge of that system. Okay, so that's kind of the XOR randomness extractor claim that we need. And this has actually also been used in follow-up work in a related context of certified deletion. Okay. Good, so speaking of follow-up work, we left a bunch of questions open in the paper, some of which have already been answered. Okay, so one of the most natural ones, right, is recall that we give this 3-message protocol, and we left basically 2-message quantum OT open, right, which would be OT without public key crypto. And this has been answered in this really beautiful protocol of Collison, Muguruza, and Spielman, right? So they exactly answer this question. They assume like a NIZK and some other hash function assumption, but they have an instantiation, right, in the QROM. Although they need to make non-black box use of a hash function, so they need to kind of assume something else in the QROM, okay? But the point is that this is the first proposal for a 2-message, kind of a round optimal OT protocol with no public key crypto, okay? And the other work I want to mention is a work of mine with Kirana and Srinivasan, where recall in our shared EPR pairs model, we were only able to achieve OT, like bit OT, where the sender transmits 1 of 2 bits. And so in this work, we improved this to string OT, where the sender can transmit 1 of 2 strings. And this is particularly important because in the setting, bit OT is not complete for secure computation, but string OT is, right? So we have a corollary that shows that you can do 1-message secure computation of any, at least unidirectional classical or quantum computation in this model, right? So if we share EPR pairs, you can just send a single message and compute any functionality in 1 message, okay? And then also in this work, we show how to do 2-round MPC without public key crypto in this shared EPR pairs model where every party starts with some shared EPR pairs. And there's still a couple interesting questions that are open in this direction, and probably more. But 2 that I want to mention are, you know, can we get 2-message OT unconditionally secure in the QROM? That is, can we obtain 2 messages OT from the black box use of a hash function? Okay, so this is still open. And then, you know, in this recent work, we do 2-round OT in the shared EPR pairs model, but it's not necessarily, you know, impossible just in the CRS model. So this is still open. Can we do 2-round MPC without public key crypto just in the CRS model? So these are some nice open questions, I think, to continue this study. And so thank you for listening, and I'll take questions.
Are there any questions? What is the communication complexity of your protocols? More or less.
Yeah, so we actually analyzed this in the paper, and we have we have a table of like various. We have a few protocols and kind of the asymptotic complexity, or actually the concrete complexity as best as we could determine. And for our 3-message protocol, you know, it's something, I forget what it is, you can see the table in the paper, but it's some thousands times the security parameter, so it's fairly inefficient, yeah.
Mm-hmm. But is that like, is that the overhead? Or so if you have like a message of a certain length, you need to send, say, like a number of states that is...
Yeah, that's the overhead, right. So even if you're just say for bit OT, you want to do a bit OT. I mean, it's linear in the security parameter, but it's some thousands times the security parameter because we're doing this like cut and choose thing, and you need to kind of do this many times in order to get a good security bound.
Okay.
Yeah.
More questions? Okay, then let's thanks James again and all the speakers in the session.